Welcome back. I hope you had an excellent weekend and you're ready to dive into some more math, some more combinatorics. Over the next few days in lecture, possibly just the next two, so today's video lecture and Wednesday's lecture in class, I would like to cover the principle of inclusion and exclusion. So the idea behind this is that we would like to generalize the subtraction principle. So if we are to just dive right in, let's talk about the principle itself. Our goal here is to do exactly that. We are going to generalize the subtraction principle. Now, if you'll recall the subtraction principle, we needed two sets. And let's say we had our big universe here, and we were able to divide that universe into two pieces. In other words, we had a big set of all the things that we could count, and then we're going to divide this up into sets 1 and 2. That's the partition. U is the union S1 and S2, where S1 and S2 are disjoint. And let's see, both of these pieces are non-empty. So in other words, something has to live in each piece. Now, subtraction principle itself said that we were going to count things in the second set by instead counting everything that we could have. So this U is the entire rectangle here. And we are going to count the things in S2 by instead counting the things in S1. And then the difference between the total number of things we could count, this U, and the things that don't satisfy the property that we want, and that's S1, we can generalize this to any size partition we want, but the fact remains that we needed a partition in order for this to work. Okay, so in order to generalize the subtraction principle, we need to be able to, okay, if we're going to generalize this, the idea behind it is that there are possibly easier chunks, easier sets, and I'll say subsets actually, to count there are easier subsets to count than those afforded by a partition. And we'll see exactly what I mean in a second here. But maybe there's a different way of dividing this set up. So here's my set U now. And maybe there's this little chunk up here that I would like. Maybe this other little chunk downstairs or off to the side. Maybe there's a set B there. And maybe there's a set C in here. That's all this stuff in red. That, and the leftovers we'll just call D. So let's call the green stuff D. So the idea here is that, yeah, maybe these sets A, B, C, and D are easy to count on their own, and D comes all the way down here. I just noticed it has to go down to touch the red. Okay, so maybe these sets are individually very easy to count on their own, but let's kind of put a wrinkle in this. Let's say that C and D further overlap. Maybe there's absolutely no way for me to use these four sets to partition U so that I can use the subtraction principle or even the addition principle. So this is the issue. So A, B, C, and D are easy to count, but don't form a partition. Okay, so this is the idea. So as with the subtraction principle, we will count everything in U, and then maybe we just want to count the things in A. So in order to do that, we count the things in U, and then we count everything else, B, C, and D, and see how badly they overlap with A. So in other words, there's a whole part in here, there's a whole mess. A is completely contained inside D, so everything that's in A is in D. So D definitely counts everything in A, but also C is going to count some things in A as well. And this little region right here in black, I would like to remove that, because that, if I count both D and C, then I'm double counting this area that overlaps in A. And this is what the principle of inclusion and exclusion actually does. It tells us how to put things into what we want to count and take things out that are double counted. But maybe you took out too many things, so maybe you'll have to add something back in and keep trading off between the counts. So here's an idea, or here's an example that's going to illustrate what we want to do exactly. And it'll start with the following question, or the following task. We would like to count how many numbers between 1 and 1,000 and 1,000 that are not divisible by, I think that says 6, 7, and 9. So by 6, 7, or 9. Okay, so here's what's going on. I need to make sure that whatever numbers are in my set that I want to count aren't divisible by 6, nor are they divisible by 7, nor are they divisible by 9. Okay, so there are lots of numbers that aren't divisible by 6. There are lots of numbers that aren't divisible by 7, but unfortunately there are numbers like 42 that are divisible by both, or there are numbers like 43 that aren't divisible by either that we'd like to include. And, well, it might actually be easier just to count how many ways or how many numbers that actually are divisible by these numbers, and then start taking out overlaps. So let's start there. Let's see. Label SI the set of numbers between 1 and 1,000 that are divisible by I. So namely, we're looking at S6, S7, and S9 particularly. The numbers that are divisible by 6, by 7, and by 9, respectively. So what we would like to do is actually count these. So it's not too hard to see that we can count S6. Well, let's see. So S6, I'm looking at the numbers 6, 12, 18, 24, 30, so on. And I know that there are at most 1,000 different options here. So what I'm going to do is I'm going to take the floor of 1,000 divided by 6. And this gives me how many numbers between 1 and 1,000 are actually going to be divisible by 6. You can argue that one for yourself, but it's really just counting how many of these numbers I can skip by 6s to count. Similarly, I can get S7's count by 1,000 divided by 7. And I'm at the bottom of the page. S9 by 1,000 divided by 9. All right. So if we want all the numbers that are not divisible by any of these, in other words, we're not in any of these sets, so just take all of the elements in S. So take everything in S, so the numbers that we want to count, or the numbers here that we want to count between 1 and 1,000. Take all 1,000 numbers that we could use, subtract out the ones that are divisible by 6, the ones that are divisible by 7, and the ones that are divisible by 9. So we're done, right? I mean, that's it. That's the subtraction principle. But yeah, S6, S7, and S9 actually have mutual intersections. For example, so nope, we are not done. Consider the number 42. 42 belongs to S6, and it belongs to S7. Oh, shoot, just lost the lights in the room. Hold on one moment. There we go. So what happens if you stay in these rooms for too long and everybody thinks you're dead and they come to clean you out at some point. The lights are just ahead of the game. Anyway, so 42 belongs to both S6 and S7. So I, in effect, took that out not once, but twice. And that's an issue. Okay, this is exactly what happens when we don't have sets that form a partition. We get these overlaps and things are removed more than they should be, or more times than they should be. So here's the deal. So if I took it out twice, let's just add it back in a clever way. So fix this by adding back in everything from S6 intersect S7. So in other words, if I took things out that belong to S6 and I took out the same things that belong to S7, well, I took them out twice, so what I'm going to do is I'm going to add them back in. If I pull them out twice, make up for it by adding the things you removed twice back in exactly once. Okay? So the way that we're going to do this, we count S6 intersect S7. Well, this is just, their least common multiple is a 42, so they're going to overlap on skipping by 42. So there's the floor, 1,000 divided by 42. Very similarly, so I'll say similarly, add back in S6 intersect S9, the ones that belong to S6 and S7, they also were removed twice, so we got to add them back in. And very similarly for S7 and S9. So they both have to be added back in as well. And these are done in S6 intersect S9. Okay, 6 and 9 have a common factor here, so they'll actually start you'll run into things that belong to both sets after you skip by their least common multiple of 18. So I'm skipping by 18s when I'm counting this. And S7 and S9 don't have, their least common multiple is a 63, so I can just go ahead and multiply that together. Oh, I want the size of that and the floor of the quotient. Okay, 63. Okay, so this number right here is 23. Oh, no, sorry. This one is a 55. This one is a 15. And this guy upstairs is a 23. If I went back to the original counts on the previous page, this is 166, this is 142, and this is 111. All right. So all I have to do now to count the things I want, well, take the 1,000, remove the things that are divisible by 6, 7, and 9, and then add back in the guys that are divisible by both 6 and 7, the guys that are divisible by both 6 and 9, and the guys that are divisible by both 7 and 9 as well, so S of 9. And now I think I'm done, but shoot, no, there are things that are divisible by 6, 7, and 9, and I just added them back in too many times. In fact, I added them back in one time too many. Okay, we'll see exactly why that's the case in a second. Let's see. Yeah. I added them back in exactly once. Once too many. But I still need to remove the triple intersection. S1 or 6, 7, and 9. Okay, and I count that one the same way I've been counting the other ones upstairs. And that is S6 intersect S7 intersect S9. I need their least common multiple. Turns out that their least common multiple is going to be 18 times 7, right? It's the least common multiple of this pair, and then the resulting least common multiple of 7 and that least common multiple. So this will be 1,000 divided by 126. And I'll take the floor. Okay, now, I think that's the only combinations of ways that I could have overlaps. Either I'm doing pairwise intersections among the three sets, or I'm intersecting all three. So, the final count. Finally, we have the size of the numbers that we want to count. It's all of the numbers that I could have counted, minus the sum of the individual, like the singleton sets, the ones that are divisible by 6, 7, or 9. So there's the 166 from S6, the 142 from S7, and the 111 from S9. But I took out too many things, so I add back in the 23 from 6 and 7, the 55 from 6 and 9, and the 15 from 7 and 9. But then I added back too many on that triple intersection, because there are things that belong to each pairwise intersection, and those number 7. All right, and that means that the final count here is 667. Phew. Okay, that was a lot of work, but the point is, we were able to count the set using easily managed chunks that didn't necessarily form a partition. And this process generalizes. It generalizes very, very readily to this thing that we call the theorem of inclusion, or the principle of inclusion and exclusion. And sometimes I'll just abbreviate it PIE. And sometimes I'll ignore the and entirely. All right, so this is stated thusly. Let U be a universe of objects that we know how to count. And this is the tricky part of the statement. And script P, right, this is just a fancy stylized P, is a collection P1 through Pn. We're going to let them be a collection of properties. That we can describe of the objects in the universe U. So a collection of properties of objects in the universe U. And we're going to denote by SI the set of objects that satisfy P. So the objects in U satisfying P, or PI. And we're going to do that for each I between 1 and n. Then the number of objects in U that don't satisfy any of these properties, so don't satisfy any property in the set P. So that number is given by the following. Now, it's very, very long to state this, so give me a moment to write it out. So S was going to be the collection of things I want to count. So it's all the things that don't satisfy any of these properties. That's given as S1 bar, so the complement of the things in S1, all the way out to the complement of the things in Sn. And this is the statement of the inclusion-exclusion principle. We have the total number of things that we could have counted minus the sums of the singleton sets. Right? These are all the things that satisfy each property individually. And then we took out too many because there may be things that satisfy more than one property. So we have to add back in the pairwise intersections. And yes, there are going to be a lot of them. So as an example, we'll go through. Oh, come on, computer, wake up. There we go. Sorry, computer screen just hibernated on me. And we'll add back in all the way out to Sn-1 intersect Sn. And we're going to subtract out the triple intersections. So these are the triples. We're going to add back in the quadruples and subtract out the quintuples and so on. We're going to keep alternating because we keep taking out too many things or we keep adding too many things back in. But we will end, I guarantee you, we will end on a -1 to the n times the size of all the things that satisfy all n properties. Okay? Now, this is kind of cumbersome to write. So sometimes you see this abbreviated. In fact, much of the time you see it abbreviated thusly. So you're summing over all the i's of all the singleton sets, so you're subtracting out that entire sum. And then you're going to add back in, for I less than j, you're going to add in the pairwise intersections. Then you're going to take out, on the next line, you're going to take out I less than j less than k, the triple intersections. Right? The fact that I'm making all these indices increase in order is so I don't double count things in my sums. And then we're going to add a whole bunch of other things until we get down to that last term. In the last term, there's only one way to intersect all n sets. And that's this fellow here. Whew. That in its entirety, let's see if I can fit it all on one page. There it is. Without the title, that's the principle of inclusion and exclusion. Awesome. Okay, so our example, we wound up using the case for n equals 3. So our example used n equals 3. And the way this looks, it's all the things that we want to count. It's given by the things that we could count minus this sum S1 plus S2 plus S3 plus S1 intersect, so S1 intersect S2 plus S1 intersect S3 plus S2 intersect S3 minus the final triple intersection, S1 and 2 and 3. Okay, our sets were labeled differently just because of the convention I chose. But it's everything that satisfied 1 or 2 or 3 that I took out of everything that I could have counted, plus the things that satisfy each pair of properties. But then I overcounted those because there are things that belong to 1, 2, and 3 of the pairwise intersections. So I subtract out all the things that satisfy all 3 properties. So that's what it looks like particularly, and for this set, for this n equals 3 example. And this is, in effect, the way that we're going to generalize the subtraction principle. Now, seeing this big formula out in its entirety is actually really scary, even to me. It's just, there's a lot of things going on there, and it's kind of, the meaning behind it is somewhat lost in the algebraic expression. So let me give you kind of, we're not actually going to prove it in its entirety, but there is kind of a slick way to at least give it some credence, some credibility, that it might actually be true. And I'm going to do this pictorially. This is by no means a proof, but it does at least illustrate how this works for the case of n equals 3. So here is my universe. It's this nice big box. Everything in U. Time for colors. S1 is going to be everything inside of this red disk, this red circle. Okay, so S1 I will mark here. Now I'm going to use green to talk about S2, and this is everything in green. Yep. And we'll mark that by an S2. And then we'll have, oh, there go the lights again. Excuse me, one moment. Okay, whitewash screen, and then we'll let it come back. Focus, 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 focus. Cool. Hey, look at that. We're already a half hour in. And then we're going to use blue to capture S3. And this will be vertical slashes. Okay, so it should be pretty clear on this nice color screen. It's not going to be like my lecture notes where I scan them into the computer and they're all black and white. No, this one, we can actually see the different contributions from each of these slices in the Venn diagram. So what I want to count is everything outside of the Venn diagram in U. But in order to do that, I know how to count S1, 2, and 3, but they don't partition that complement. So I notice that there are 3 different regions, or sorry, there should be 1, 2, 3, 4, 5, 6, and 7 different regions. There is this S1 only region, right? This guy right up here. He doesn't overlap with anyone else, so he contributes exactly 1 to the count in the principle of inclusion and exclusion. Very similarly, there's a S2 only that contributes a 1 to the count. And then there is an S3 only that contributes only 1 to the count. So that would be these regions right up here in the top left, the top right, and the very bottom of the Venn diagram. Now in between them, there are things that are counted exactly twice, right? And these are just the pairwise intersections. There's in here, if I count red and I count green, that means that the red and green pieces are counted twice. Very similarly, I can fill in the rest of these spaces in between that are the pairwise intersections that all contribute 2 to the count. And then there's one final piece in the middle that is the triple intersection, and this contributes 3 to the count because it belongs to 1, 2, and 3. So the idea behind this picture is each region has a number in it that counts how many times the big disks overlap it. Now, if I were to take out, or if I'm just going to count the union here, I have 1, 2, 3 that are counted from putting in S1, 2, and 3, but then that overcounted these 2's. So I take each and every one of them out. But unfortunately, that means that these actually extend, the pairwise intersections extend into the center of the Venn diagram. And I removed these things all 3 times that they were added. So I added everything in S1, S2, and S3. So just considering this middle piece, it's added once by S1, once by S2, and once by S3. And it's removed once by S1 intersect S2, removed once by S2 intersect S3, and removed once more by S1 intersect S3. So for each and every time that I put it in, the pairwise intersections took it out, which means I have to add this little piece back in. And that's effectively what's happening in the principle of inclusion and exclusion. You're counting how many overlaps you have and how many times they were overcounted. But in general, so generally speaking, the SIs contribute n choose 1 to the count. Okay? The SI intersect SJ pieces will then take away n choose 2 counts. Okay, so this brings me back down to being in the negative. Like I took away too many things and I have to get back up. The SI intersect SJ intersect SK pieces are going to add back an n choose 3 to the count. And I can continue this, taking away, adding back, taking away, adding back, until I see S1 intersect all the way out to Sn for n many pieces. It's either going to add back or remove n choose n counts. So what does that total look like? So the total number of counts will be n choose 1 minus n choose 2, add back in the triple intersections, subtract out the quadruples, and so on, until I hit the last one, where I am adding back in or taking back out all n of these. Now, this should be an n minus 1, and we'll see in a second why. This will be, right, because I started on a 1, not on a 0 index. Okay. By the binomial theorem, we know that this is n choose 0. Right? This is exactly the sum over here, minus 1 to the n times n choose k. K ranging from 0 to n. This is the same thing as 1 plus negative 1 to the n, and that's 0. Okay, so that means that everything in here was counted exactly once. There are no overcounts, there are no undercounts. So everything lives in at least one of everything is going to be divided up into this new partition where everything is counted exactly once. So even within the context where we don't have a partition, we were able to take the Venn diagram and split it up into a partition. This is just what the addition principle looks like on that union, right? And I'm framing it in terms of pieces that are easy to count. All right. So we should probably continue with more examples now, just to really hammer home how this works. So new example. How many permutations of the letters, and bear with me here, good news, everyone. Explain it to your friends. Okay, so I'm going to permute all of these letters, and for reference, this is the multi-set, let's see, it's D, 4 E's, 1 G, 2 N's, 3 O's, 1 R, 1 S, 1 V, 1 W, and 1 Y. So that's the multi-set I'm working with. So how many permutations of those letters are there? And now I'm going to be restrictive, such that none of the words, and these are going to be subwords, none of the words good, news, and everyone occur as consecutive letters. All right, so this seems pretty darn hopeless. So if I want to make sure that none of them show up, it's actually not that hard to count how many ways there are for exactly this combination, these combinations of letters to show up. Either the good, the news, or the everyone. I can just go ahead and treat all of them as one glued chunk and then count the permutations of the leftover pieces. So let's use the principle of inclusion exclusion to do this. So that's PIE for the properties P1, and this is good occurs in the permutation. P2 will be news occurs in the permutation. And property 3, everyone. See, you all are involved. Everyone's included in the permutation. All right. So we're going to use that collection of properties, and we're going to use some shorthand notation here, some set notation. S sub I is going to be defined as all the x's in U, and I'll define U in a moment, such that x satisfies PI. And that is where U is the set of all permutations of the multiset above. And this, I'm just going to go ahead and name this multiset M. All permutations of M. Cool. So that's our setup. This is again an instance of the principle of inclusion and exclusion where n is equal to 3. So let's run through this. We're going to have to count a whole bunch of sets. So PIE first says that to count everything I want, and this is just, I'm calling it S, I'm going to count everything in U, subtract off all the singleton properties, S1, S2, and S3, and then I'm going to add back in the properties that are shared between the ones that share properties S1, 1 and 2, the ones that share properties 1 and 3, and the ones that share properties 2 and 3. And then I'm going to subtract out the ones that share all 3 properties. Okay, I know I got crammed at the end there, but it's on the previous page. It's on, if you want to, previous 2 pages ago, if you want to see it. I think that was almost 10 minutes ago at this point. Whew. So let's count S1. So S1, not money, S1. So the way we're going to count these multisets, I'm going to go ahead and glue the word, glue these 4 letters together and treat it as one single letter, and I'm going to call that letter star. Okay? So that then leaves me this. I now have a new multiset, and I'll call it M sub 1 is now going to be star and then news everyone. And this is going to be a brand new multiset. Okay, and we can count the permutations of M1. So perms of M1, I can count using the multinomial coefficients. And let's see, E is repeated 4 times here. I think there's also a 3, a 2, and there are quite a number of 1s left over. Let's see, who is repeated? E is repeated 4 times. Looks like N is repeated twice. W, S, R, and Y all get a 1 count. Who gets the 2? Who gets the 2 count? Well, the N gets the 2. Who gets the 3 count? 3 count. News, everyone. Oh, maybe that's not right. N is counted 2 times. E is 1, 2, 3, 4. W is once. S is once. V is once. Yep, so I only have I don't have that 3 count in there. Right, I removed two of the 3 O's. That's where the 3 came from. Whew. Okay, so that's the multinomial I have. I'm probably going to have to compute that one because that's wrong in my notes, but it's correct here. All right, so we're going to use a very similar methodology to count S2 and S3. So now we're going to glue news together. So news is now star. And we're going to take out news from M. And so news is now the star. And now permute the set M2. Star, good everyone. And the computer just hibernated on me again, so excuse me a moment while I bring it back to life. Hello. There we go. This can be done in, let's see. Oh, and now the backlight. Oh, killing me, technology. You are killing me. Permutations of M2 can be counted using the multinomial coefficient. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total letters here. Right, and the star accounts for one of them. Okay, the star, let's see. I get 3, 3, 1, 1, 1, 1. So that's 6, 7, 8, 9, 10, 11, 12, 13. Whew. Yes, I have to include all the ones because I need to make sure that these numbers downstairs actually add up to the 13 upstairs. Okay, and finally, we count S3 by taking out everyone. Everyone is now star. Everyone's a star. And this creates M3, and we permute that as, oh, now we change the total number here. No longer are we dealing with 13 letters in total. I took out 8 from a total of 16. So this is actually 8 remaining letters and 1 star that corresponds to everyone. So this is 9. And then I'm permuting, let's see, O is repeated twice, everyone else gets a 1. 1, 3, 4, 5, 6, 7, 8, 9. Whew. All right. So that's how we wind up counting the singleton sets. And you know I would be asking you to hazard a guess in class as to what we do next. And yeah, I don't have you there, so we're gonna play like I don't know, maybe a kid's show. Shout at the screen. What should we do next? Ah, tell me. Yay. Okay. You're right. No. Okay. So count S1 intersect S2. We're gonna do this by now gluing together not 1 but 2 collections of letters. And I need to distinguish the gluings. So call good star 1. And news, you're going to call that one star 2. Now we permute what's left over. Permute this multiset, star 1, star 2. Those are different letters, that's why I have to distinguish them. Right, they're different combinations of good and news. And then all that's left is everyone. Everyone is left. Okay, so now we can permute these. In how many letters do I have? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. And it looks like the E's are the only things that repeat. 3, 4, 5, 6, 7, 8, 9, 10. I'm going to permute those in that many ways. Cool. Similarly, count S1 intersect S3 using the same method. Star 1 is still good. Still good. And star 2, or star 3 now is everyone. All right, so then we can permute star 1, star 3, and then, well, I used good, I used everyone, so all that's left is news. And there's a total of 1, 2, 3, 4, 5, 6 different letters here. All of them are distinct, except for, well, no, they're all distinct. And we're going to do this in, well, it's 6 factorial ways. And this is exactly the multinomial coefficient 6. 1, 2, 3, 4, 5, 6 ones. And we're going to do that in that many ways. Okay? And to count S2 intersect S3, we're going to use the same notations. Star 1 is no longer part of this, so it's just stars 2 and 3. So we're going to permute the following set. Star 2, oh, not star, star 2 and 3, and then the letters that are left over are G-O-O-D. And we can do this in, well, there's 6 letters in total, and 2 of them are repeated. Everybody else is a singleton. You can do that in that many ways. And that's all the pairwise intersections. Finally, we count the triple intersections. S1 intersect S2 intersect S3. And this is literally just permuting the stars. Star 1 through 3. So 2 and 3. And we know how to do this. This is 3 factorial ways. Okay? Not too shabby. So those are all the individual counts. What do I need to do with them now? I need to actually apply inclusion and exclusion to do this. And I'm not actually going to count these out because the tolerance on most mobile devices is not this high in order to be able to count any precision. So if I'm going to write this as a response, I'm going to say take everything, all the permutations I could have had, so 10, 11, 12, 13, 14, 15, 16 total letters with those repeats in the bottom. Those are the total number of permutations of that multi-set, good news, everyone. Then I'm going to take out the singletons, so 4, 3, 2, 1, 1, 1, 1 from S1. 3, oh, sorry, that was an extra 1, right? My notes were wrong again. And then 3, 3, so 7, 8, 9, 10, 11, 12, 13. And then 2, 1, 1, so 4, 5, 6, 7, 8, 9 from 9 letters. Whoop. And that counts, so that was S1, S2, and S3. And now I have to add back in the pairwise intersections. Those go as 3, 1, 1, 6, 7, 8, 9, 10 among 10 letters. That was S1 intersect S2. And then I have, let's see, from S1 intersect S3, that's 1, 2, 3, 4, 5, 6 ones and 6 letters. And then S2 intersect S3 gives me 2, 1, 1, 1, 1 among 6 letters. And then I subtract out 3 factorial for the triple intersection. Now, basically, what this does, this is just some huge, gigantic number. So all I can really say is that I can just give you a relative size. So the number of the number of things I wanted to count, where none of good, news, and everyone appear in order in the permutation. This accounts for, let's see, if I divide that over my universe, this is approximately 99.7% of all the permutations. of u. So in other words, if you are to pick a random permutation from u, the odds of you getting a permutation such that good, news, and everyone never occur as consecutive letters is nearly all of them. There's only about 0.3% of all the permutations that will have good or news or everyone as consecutive letters. Sweet. Okay. Now we're still in section 1 here. Now is about the time where I would tell you to take a break. So you're welcome to go ahead and pause the video and come back. This is a good stopping point. We're just going to do one more example when you come back. Let's see. So now that you're back from break, I love video editing. It's great. Now that you're back from break, there's a way that we can kind of cheat this, because in the previous example, it was actually ridiculously hard to count these individual sets when they're all being counted in different ways. So it actually turns out that if these intersections are the same size, so at each level, so the singleton intersections all have the same size, the